Welcome everybody this afternoon in Lausanne for the new installment of this CECAM and MARVEL Mary Ann Mansigh Conversation series. This is a periodic set of events that actually we started online during COVID together with between MARVEL and CECAM, and we keep them hybrid. I think it's a good opportunity for people who are way to take part and intervene in these events, but also then we have here the attendees from that can come to our room here in CECAM. And today, this series is about exploring the impact that computation and modeling has beyond the strict scientific domain to understand the importance that it has in different societal aspects. And in today's installment, it's a pleasure to welcome Erich Wimmer, who works recently from materials design, so he's really an expert in the communication and understanding what are the needs of industry from the point of view of computational modeling, what they bring. But I should say that Erich is unique in the sense that he has a very solid scientific background. He got a degree in Vienna, and then he spent quite a number of years in the States at Northwestern University, and later on also at Cray Research, Minnesota, where he was both involved during some time in the development of methods to the study of properties of materials and surfaces, and also then more recently, during the last years, he has been working in materials design, leading teams in the development of computational models for material prediction of material properties. So I think he has a unique standing position to understand, to have seen along his career the development of modeling, both from the point of view of what it brings to our understanding scientifically, but also in terms of the importance and the potential use that it has for companies. So I'm sure today will be an opportunity to share with us this view, and then let us understand the value of computation and modeling and probably what lies ahead of us. Before we start, just as usual, a couple of slides of advertising for CECAM and MARVEL. We organize this series periodically, but we also organize other type of events. So I wanted to mention that in the near future, in the month of May, there will be a distinguished lecture organized by MARVEL, and the next speaker will be Alan Aspuruguzik from Toronto. He will talk about that there is no time for science as usual, materials acceleration platforms. Maybe we will listen something about that also today. And then at CECAM, we also organize periodically the Mixed Gen series that's oriented or thought for young researchers in heart. And then typically we invite an experienced speaker, and then also younger or earlier career researchers have the possibility to share their results. And the next series, the invited lecturer will be Lucia Reining from the École Polytechnique in Palaiseau, and she will talk about electronic energies beyond density functional theory. I also wanted to mention that there is a special event that will happen this summer here in the EPFL campus. That's the Psyche conference that is organized periodically. This one should have happened already, but because of the COVID, it was delayed. I think it will happen presentially this coming month of August, between the 22nd and the 25th. And this is the largest conference worldwide in first principle simulations. It will be 3 days and a half. And actually, May 31st is the deadline for early bird registration. So here you see the address. So if you want to connect, if you Google Psyche 2022, it will be there. And I encourage you also to visit the website and see if you are interested you are still in time to register. Now, after these announcements, a couple of pieces of information on how this is going to be organized this afternoon. We try to get a relatively flexible format to get in the environment to discuss and to have a possibility to talk with Erich. So there will be first a presentation by Erich, Fascination and Industrial Value of Materials Modeling. Then there will be a moment for questions and answers on his presentation. And after this first part, then there is a second part, which then will happen here on this table, which is more an interview and recollection. So it will be a more informal conversation that will be moderated by Bill Corton, who is professor here at the EPFL, and who is, it's a pleasure to have him here with us. And then we will finish at 5. For those of you who are physically here, then there will be an aperitif to finish off and also give you the opportunity to approach more directly Erich if you wish to. Now, for these hybrid events, it's important a bit to, I mean, we are used to them, but just to understand the etiquette on how we should behave. For those of you who are remote, you are joining through a Zoom event. You cannot activate your video or your mic. You cannot use the chat. All the communication between you remotely and us here in the room is through the Q&A channel. So both for the questions after Erich's presentation and for the interview and the dialogue with Bill, you can pose your questions anytime. And then here we have Sarah Bonella, the CECAM Deputy Director, and Patrick, who is supporting MARVEL, who will take care of reading your questions and then passing them accordingly as the event evolves. And for those of you who are here, when we have the questions, then you can naturally ask the questions as we normally do for face-to-face meetings. I think that's all from a technical side. So after this introduction, we can now move on to the body of the event. And then, as I said, the first part will be the presentation by Erich. So please now, Erich, the floor is yours.
Well, thank you very much for this kind introduction. Now, this is very special for me because this is the first time in 2 years that I'm actually giving a lecture or having a meeting with real people in front of me, not just a screen with some people somewhere in the world. However, I should say that I'm very pleased that you organized this hybrid event, so also welcome to all those who are watching here on their video screen and computer screen. I should also say that the last time I gave a physical meeting and presentation was in Switzerland I think it was early February, the year of 2020, just before the COVID hit us. So I don't know if there's a meaning to it, but the first one after COVID is again in Switzerland. Yeah. So, but without further ado, let's jump into this lecture here. And I've selected as a title 2 aspects. The fascination, which is kind of the human aspect, and the industrial value, which is the practical consequence. And so, but before I start, I really want to appreciate and acknowledge all those who made this possible. And of course, as always, these kinds of efforts are a team effort. So I want to express, first of all, my thanks to all the customers of our company, Materials Design. We are serving over 700 different customers worldwide, including many, many big companies worldwide. And without them, well, I just wouldn't be here. Then we have science technology partners. And in particular, we have a very strong relationship with the group of Georg Kresse, VASP, in Vienna. Well, I'm originally from Vienna, so I'm kind of biased. Yeah. And then, of course, I want to thank all my colleagues at Materials Design. They're listed here. Let me see. I think that should work here. Yeah. And in particular, one who is actually joining us here, Leonid, came to our company last October, it was, October 15th, if I remember. And he has done incredible work since. I mean, together with all my colleagues, it's a real team effort. So, the first question I would like to address is, why are we humans fascinated by modeling? Why are we doing this? And then so what is the value? And so those will be more general considerations. And then I will jump into a topic which has great urgency and importance. That's energy. And there will be aspects of structural materials related to nuclear power plants and their safety, batteries, electronics, and the environment. And then we just wrap it up. So fascination of modeling, it seems, if we stretch ourselves a little bit, any kind of art where you try to capture nature is already some sort of a modeling. So, of course, you recognize this painting here from Lascaux, some 15, 20,000 years ago. Artists tried to kind of model basically their environment, the animals. We can think about modeling of, architectural objects. That's actually from my brother. He's an architect, and that's a hospital in Luxembourg. Then, of course, as solid-state scientists, we try to think about structural models, sodium chloride structure. Of course, when you talk with biologists, they show you this wonderful double helix and proteins interacting with a double helix. Of course, we all know the Watson-Crick double helix. In a sense, also modeling could be seen as, in an abstract way, when we cast nature into formulas. And that's probably the most powerful and most abstract form of modeling, where with these few symbols, you capture basically all of chemistry. So in other words, modeling is very, very deep rooted in the human nature. Why do we do modeling? We have the desire to understand. Now, look at from a linguistic point of view, understand. It's not overstand or bystand, it's understand. In German or in French, comprendre. So kind of, probably in Spanish it's similar. So you want to get your arms around something. And the Germans are even more direct. They want to touch it. Begreifen. So that's something very, very deep in modeling. And so why are we doing that? Well, because if we understand something, we can predict. If we can predict, we can imagine new things. And if we can imagine things, we can also create them. Perhaps another aspect which is not explicitly stated here is we do modeling also to communicate. Because if you want to explain to your colleague, well, I have this idea and I'm thinking about, you go to the board and draw something, or you show some model. So it's also a way of communication. Yeah? You could say, well, I think, therefore I am, I think. So after these kind of very general thoughts here, let's go to the technological aspect and societal aspect. It was Volker Heine who actually gave me a book written by David McKay, Renewable Energy Without the Hot Air. You can download it for free on the internet. It's a beautiful book. I mean, sadly, McKay died of cancer a few years ago. But he simply asked the question, can a country like the United Kingdom provide all its energy needs from renewables? And he goes very systematically through all the possibilities, be it geothermal, solar, wind, tidal waves, and tidal changes and waves, and of course all the other sources. He comes to the the basic conclusion that no, it doesn't work for the UK. And he also makes the statement, well, don't believe I'm pro-nuclear, I'm just pro-arithmetic. So where does the arithmetic come from? Well, when you look at where do we spend our energy, and so we, on average here, a European, a Western European person, we spend something like close to 200 kilowatt hours per day per person. And where does it go? Well, it's kind of sobering. A lot of it goes in transportation, car transportation, and jet flights. Flights are very expensive. And another major chunk, of course, is related to housing, meaning hot water, heating, and cooling to some extent. Then there's a big chunk here, McKay calls it stuff. Well, we can also call it industrial production. So if you look at your table, well, someone has to produce it, it consumes energy. Someone makes this concrete here, someone makes the paints, and on, yeah? So that's where it comes from. So in other words, if we really want to be more economic about energy consumption, transportation and housing is a major part, and industrial production. Now, amazingly enough, look at lighting. It's basically peanuts. Doesn't matter, basically, in the big scheme of things. So if you say, oh, I have LEDs and now I'm really green. Well, as an engineer, you say, well, okay, fine, it's good. I should do it, but it doesn't change much. You should look at here. You should look here. And then ask, well, what does the energy, the primary energy, come from? And this is the last 20 years, the trend. Coal, oil, natural gas. We are burning the fuels, the fossil fuels that nature has given us and created over the last 200 million years. And we're about to burn them in about a few hundred years. That cannot go on. I mean, that's really the tremendous challenge that we have. Yes, we have nuclear with all the caveats, all the dangers, but also all the promises. We have hydro. I mean, Switzerland is in a very, very good shape here. Now, you go to Barrage de Dissens, fantastic geographic. You get several glaciers feeding into this, and then you have basically 1,000 meters a difference between the power stations and the reservoir. And of course, I admire that the Swiss, I mean, they buy during the night the cheap nuclear energy from France for next to nothing, pump the water up there, and then when everybody needs electricity, they open the valve and sell it for mit erheblichen Kosten. So that's hydro. And then there's others. Now, clearly, there are wind turbines, there are the solar, but they're intermittent. And what we forget is behind each wind turbine, you need a gas turbine. So the gas people love wind turbines because it's intermittent and we don't have good, sufficient energy storage. Yes, you can pump energy. But so those are really the challenges, and that's reality. And we all witness the geopolitical consequences of that situation here. So, with that, let's jump in. What can we do with materials modeling? And what is actually being done? Really, one of the driving forces is, well, reducing energy consumption and reducing CO2 emission. Now, we work quite a bit with the Electric Power Research Institute in the US. It's a non-profit organization that organizes pre-competitive research among all the power utilities. So that, especially in the nuclear field, there's a lot of sharing of information because nobody wants an accident. And so, I mean, here's the kind of the physics fascination. When you look at the energy content, coal, you're burning coal, you're getting about 4 times 10 to 2 kilojoules per mole out of coal of this reaction here. And if you make fission of uranium-235, you're getting 8 orders of magnitude more energy. Now, translate that into mass. So you have, let's say, a piece of coal. Well, the equivalent of energy that you have, you can almost put it on a single pixel here. So furthermore, when you burn coal, you're producing CO2, coal or other fossil fuels. Where does the CO2 go? Well, it first goes into the atmosphere. And when you look at, especially from space, at our atmosphere, it's extremely subtle and vulnerable. Now, on the other hand, if your nuclear energy, yes, you get nuclear waste, and there are ways to manage that and also reduce it, but it ultimately ends up in the ground, and you're polluting the lithosphere rather than the atmosphere. So again, a choice to make. I mean, there's always going to be some downside. So, furthermore, we say, well, why not going after fusion? And we all know that this big project, a global project going on in Cadarache in France, on the ITER, which is essentially still a big physics experiment. Yes, it's a step towards fusion energy. There's an effort in the UK on fusion energy, and of course, fusion energy, the jet has been successfully demonstrated. It works. The Chinese have demonstrated they can run it for several minutes, and it's real. But think about it. In fusion energy, and the easiest, in inverted comma, reaction is deuterium and tritium, giving you helium with 10 to the 8th kilojoules per mole, and neutrons. So 10 to the 9th kilojoules per mole of energy that's released in very fast neutrons. And that's a problem. How do you convert these very fast, dangerous neutrons into usable energy? Well, you bombard it and absorb it by, for example, tungsten. Well, you can imagine the radiation damage that's caused in the tungsten and all the problems. And it will activate everything that's around. Yeah? So while it doesn't produce directly nuclear waste, it will activate, it will turn cobalt and iron and everything that's around into some radioactive isotopes. So again, very promising, should absolutely be done, but let's be careful. So now let's come back to the traditional nuclear power plants. And let me just give you a glimpse on how this, what a core looks like. For example, here in Switzerland, there are some boiling water reactors. And essentially, what you have is the fuel itself are these pellets. They're uranium dioxide. They're stacked into these cladding tubes. They're about 4 meters long. And they're made out of zirconium, or actually a zirconium alloy. Why zirconium? Well, because zirconium is basically transparent to neutrons. So the neutron cross-section is quite low. So that's why, because you need the neutrons to go across to get the chain reaction going. And it has quite good corrosion resistance, mechanical resistance, and well, that's what the industry standard has become. And especially after Fukushima, there's a lot of effort to say, well, can we improve the safety of these cladding materials? And I'll come back. So one possibility is why is that, and I'll come back to that in a second. But one of the problems of any kind of material that you put in a reactor is you have neutron irradiation causing irradiation damage, and radiation damage can lead to dimensional changes and deformations. Zirconium, as you might recall, is HCP structure, so it's anisotropic by nature. And when you irradiate it, it expands in A, so in the planar directions, and shrinks in the Z direction. Because of the tubes, that they have some texture from the manufacturing, that can lead to deformation. Now, these fuel tubes, this cladding, are bundled together in these fuel bundles, and in between you have these control blades, basically boron-containing steel that absorb neutrons so they can control the reaction, but you need to move them up and down. So if you get these channels deforming because of irradiation, then your control blades may get stuck. Now, that's not a good thing to happen. So you need to understand what is causing this deformation. So that was one topic. So how do you model that? Well, here's the experimental fact. That's pure crystalline zirconium. It has a very funny unit, actually, that the nuclear folks are using, dPa, displacements per atom. So how often does, on average, an atom in your sample get kicked up by a neutron and displaced? So, for example, you start out, and then you see that it expands in A, contracts in C, and there's a plateau, and then breaks away. And it's this breakaway which is very weird. So what's going to happen? Well, we did some modeling here and said, well, you take zirconium and, when a neutron hits the material, it creates a so-called cascade. But when the cascade settles down at the end, you have so-called Frankel pairs. So you have vacancies and interstitial atoms. Okay, so in the modeling we said, let's not worry about the cascade itself. Start out with a bunch of these Frankel pairs. And then perform some molecular dynamics and see what happens, because these self-interstitial atoms diffuse much faster and anisotropically compared with the vacancies. So very spontaneously, you see that the system evolves this kind of clusters, these nanoclusters. They are the beginning of what could be called so-called A loop, dislocation loop. And when you then look at how does this change the dimension of the material, well, it contracts in C and expands in A. So probably this first part is caused by this formation of these A loops, and then they accumulate and modeling the breakaway that involves then vacancy C loops, and we've also addressed that. But here the challenge is, well, you can do molecular dynamics, you get a good interatomic potential, and well, Bill is a great expert in that, right? Even for zirconium, right? But that gets you, well, maybe in the nanoseconds or so. It takes much longer to develop these microstructures. So that's a modeling challenge. I'll come back to that at the end. And so these self-interstitials, they diffuse fast. Now, there's empirically we know that you can create niobium alloys of zirconium. And what is niobium doing? It does quite a few things, but one of that is when you look at the diffusivity of self-interstitials without niobium, well, the slope of this mean square displacement is, of course, the diffusion. You add 0.5% niobium, poof, stops. Niobium pins the self-interstitial diffusion. And so when we talked about this to our friends at EPRI, they said, well, this is great because it takes right now about 20 years to get a new material in a nuclear reactor certified and approved by the Nuclear Regulatory Commission. And they always ask the question, well, when you make an alloy, do you understand what you're doing? And they said, well, this was a nice piece of information. Yeah, we know what niobium, among others, is doing. But there's another problem with the zirconium, and that's a nasty one. You get this oxidation with water, because you have hot water under pressure, and it detects zirconium and forms zirconium oxide and hydrogen. Now, actually, what happened in Fukushima when we lost the primary, the cooling of the system. And then it takes a day or so, it heated up, and when it reaches 1200 C, this reaction starts really taking off. So you get violent oxidation of zirconium. Basically, zirconium starts burning and producing hydrogen. Well, you mix it with a little bit of oxygen, and well, that's what we saw. So how can we control that? And in particular, during operation, this hydrogen, if it goes actually into the zirconium, it embrittles because it forms hydrides. That's nasty. So it's called hydrogen pickup. And understanding hydrogen pickup is a very important topic. So we worked on that. So if you take an oxide and expose it to water, then in case of zirconium oxide, nice quantum mechanical calculations show you the water molecule dissociates on such a surface, forms kind of OH bond here, and the other OH group goes onto the unsaturated zirconium, and you've basically hydroxylated the oxide. And then you can have this hydrogen diffusing along, and that was the common wisdom of hydrogen transport through the oxide into the metal. And then we said, well, wait a minute. What about the following situation? If you had, for example, a little crack in the oxide, and in the oxide you have a vacancy, what will happen? Well, the water molecule will interact with the vacancy. It will immediately remove this oxygen from the water, and the oxygen goes into the place because this oxygen is very happy in zinc oxide. And then you have the two hydrogens. Now, the two hydrogens, they're kind of, and that's what quantum mechanics is telling us, have two types. There's one which is kind of we can call it acidic hydrogen, so it's slightly positive, but then the other one binds to the zirconium and is negatively charged, so it's hydridic. Now you have two hydrogens, one positive, one negatively charged. Well, they like each other, form a H2 molecule, and off it goes. So now you have basically a reaction of water with a vacancy forming right away molecular hydrogen. Now, if that molecular hydrogen continues and diffuses into a crack, it may reach down all the way to the metal oxide interface. And there was some beautiful experimental work done by the group of Chris Grosvenor in Oxford using TEM, showing that indeed close to the metal oxide interface you do see nanopipes and nanopores. But the trouble is with the TEM, the resolution is, well, a few nanometers. But what the simulations then showed us, that it is enough for this cracks or pores like 1 nanometer for hydrogen to diffuse. Let me show you how this looks like dynamically. Wonderful that it works. Hopefully it comes through also over the internet here. So here you have water under the conditions in a nuclear reactor, so 360 C approximately and 100 bars. And then, of course, the water goes into such a crack, wets the surfaces, and diffuses in. And for that, you can basically work out what is the effective diffusion coefficient. It's slower than in bulk water because of the reduced dimensionality. But what happens now if this water molecule interacts with a vacancy and creates a hydrogen atom, a molecule, and then you will see that these hydrogen, look at these guys here, they diffuse like crazy. Yeah? So, in other words, this could be one of the mechanisms that hydrogen gets close to the metal oxide interface. Now, this whole thing hinges on our ability to predict the microstructure, to predict the formation of these kind of cracks. And that's why we hired Leonid and said, well, Leonid, why don't you work out a way to take as input all the wonderful stuff that we get from ab initio and from molecular dynamics, like chemical potentials and mechanical properties, diffusion coefficients, grain boundary energies, and so forth. We give you all that, and you put it into a phase field model with mechanics, and that should come out. Reminds me of a saying of Seymour Cray. Seymour Cray was once asked, Seymour, why do you hire always young people? And he said, it's very simple. They don't know that certain things cannot be done, and so they just do it. I think Leonid has made tremendous progress in the last 6 months, and we're getting close in collaboration with Professor Anta El-Azab at Purdue, it has to be said, that we're creating a kind of a microstructure, phase field mechanical or chemomechanical model that will allow us to predict the oxide growth and the formation of these type of nanostructures. And zirconium oxide is interesting because it exists in various forms. You can have oxygen saturated alpha zirconium, high solubility, 25%. Then it forms a metastable monoxide, then a tetragonal phase, and finally the monoclinic phase. And they all have different properties and different volume, and especially the monoclinic is less dense, so it expands. So if you get a phase transformation from tetragonal to monoclinic, it's like an earthquake. So, let me see how I'm doing in time. Probably I'm running too long, right?
You have half an hour.
Okay, wonderful, because there's still quite a few things to tell you. Electronics. You would think that we're making a big jump here. And by the way, with that device, you can get a Nobel Prize. It is Jack Kilby's first integrated circuit. Done in 1958 at Texas Instruments in Dallas, Texas. He was a newly hired young scientist, a young engineer, didn't have any vacation. So he was there in the summer, everyone was gone. He said, well, let's try something useful, and I create an integrated circuit. Again, probably nobody told him that it cannot be done, so he just did it. When his boss came back from vacation, well, let me show you something here. When you walk into the TI lab in Dallas, they show you this work done by Jack Kilby. So we actually had a couple of years ago discussions with Texas Instruments, and they said, well, we are working on so-called green devices, meaning we want to reduce the power consumption. How can you do that? Well, number one is you reduce the size of the device. And we are currently moving towards devices that are not planar, but the so-called FinFETs. So you're down to the 10, 20 nanometer scale. So that's one thing. The other one is, if you have a metal oxide semiconductor, you want to tune the alignment of the Fermi level of the gate metal, which turns out to be titanium nitride, a beautiful material. It has a golden color, very, very nice. So that's the gate metal. And then you have the oxide. Because of the reduction of the size, the industry had to go to so-called high K dielectrics. So the winner that you probably have in your devices is hafnium oxide. Hafnium oxide, same structure, same crystallography, same chemistry basically as zirconium oxide, monoclinic, tetragonal, same structure. Here's the link between nuclear energy, oxidation of zirconium cladding, and high K dielectrics. And then you have the channel. So if you can tune the alignment of the Fermi level of the gate with that of the semiconductor underneath, and you need to do this for both for the P and for the N, then you can reduce the power consumption. And then there's a third option that you have, is you do have a contact between kind of a copper wire and the channel, and that's usually very heavily doped silicon like or nickel silicides. And you want to minimize the Schottky barrier between the semiconductor and these heavily doped. So there are also tools we have addressed that. But let's focus on this issue about the gate metal here and the alignment of the Fermi level. So schematically, you have a channel, for example, silicon, and you have a band gap. You have the gate metal that has some Fermi energy, and schematically, this is related to the band edges in some way. So what you want is for the N-type, for the P-type, where you have a hole, you want that Fermi level very close here, so that by changing this just a little bit, you can turn this on and off. And similarly, for the N-type, you want to move it up here. Now, that is a little bit harder. So you need, so that's lowering of the work function, but this one here is increasing the work function. That's the hard one. So empirically, what they found is if you deposit hafnium oxide and then deposit titanium nitride, so you form this contact between the gate and the oxide. If you then expose it to oxygen, you increase the work function. And the engineers there said, so obviously what's happening is that titanium nitride, as you deposit it, has nitrogen vacancies. If you pump in oxygen from the outside, you're filling the oxygen, you're filling the vacancies with oxygen. That must have an effect. Well, it makes sense. And we were in dialogue with the guys in Dallas, and they said, well, can you model that? Well, in a moment of weakness, we said, oh, sure. So this was the first model, and we said, well, let's create a model of titanium nitride on hafnium dioxide. First, we asked them, do you know hafnium dioxide? Which form do you have? They said, well, we don't know. It's probably amorphous. Okay, well, we said then we take the monoclinic phase, which is the stable phase, and take the surface that's the most stable surface. And that's our model, and put the titanium nitride down here. That gives us a kind of an electrostatic potential, and that you do this macroscopic average, and well, you get this baseline. Then we said, okay, well, if it's true that you add oxygen into tinitride, we should see a change. We put it in, and nothing happens. Well, when we presented these results, I still vividly remember that the manager, Judy, sitting there, said, this is modeling. I mean, you know, this it just doesn't work. Yeah? But there was one guy, Jim Chambers, who said, no, wait a minute, we're not yet at the end. And then we looked closer. And also from a physics point of view, you say, well, wait a minute, if you have a metal, and inside the metal you're changing an atom, why should that change the potential at the interface? So let's have a closer look at the interface. And then we said, what's really happening here is the following. You have the oxide, the hafnium oxide, that has a few vacancies still on the oxygen side. You have the tinitride, and you're pumping in oxygen. Now the oxygen will occupy the vacant sites in titanium nitride, but push the nitrogen towards the hafnium oxide. But the calculations tell us that nitrogen will not go into the hafnium oxide, it will get stuck at the interface. So you're piling up nitrogen at the interface. So we said, okay, here's what we do. We just take a model and replace just at the interface the oxygens by nitrogens. That's all we do. And lo and behold, you get a big change in the effective work function. Well, the reaction was, wow. So the modeling can really tell us something here. And we published that, and unfortunately, Texas Instruments later on gave up on this development. but it was a nice story. And so in other words, if your model predicts something that seems to be in contradiction with experiments, don't give up. Question the experiments. Or quoting my mentor and late Art Freeman, never trust an experiment unless verified by a good simulation. Well, I can say this here at CECAM. Okay. Another way related to energy is energy storage, batteries. We've made tremendous progress over the last 20 years in our batteries. I mean, our laptops, our cell phones, and many other devices live and die with the batteries. Mine seem to have died right now. In any event, but gracefully, not like this here, where a laptop that just blows up. And very recently, I think in the last few weeks in Paris, they are running buses with lithium batteries. And two of the buses just burst up in flame. Nobody was hurt, those are dangerous devices. So what do we need to do? And here just one example that was done with Toyota research in Belgium, actually, where there was a very brilliant experimentalist and Fabio Rosciano, and he said, well, one of the problems of these cathode materials is that you're pumping in lithium and you're taking it out. So when you charge it, you take out the lithium from the cobalt oxide, manganese oxide, nickel oxides. Cobalt oxide is kind of the prototype. And if you do that, the material expands. And if you pump in lithium, and now between these layers you have lithium plus, it actually contracts. So you get these grains breathing all the time, and eventually it breaks, and you're losing contact. And so the question, can we find materials, cathode materials, that do not breathe if you charge and discharge, and yet have a good electrochemical behavior? And there we did a series of DFT calculations, essentially looking at the different, those are spinel type compounds. And yes, we did predict 3 compounds that sounded interesting. And of course, when you predict a structure with a certain mixture, you never know if you can actually synthesize it, or if there's another phase that is more stable and the phase separates. But Fabio was able to synthesize one of these compounds that we suggested, and it worked. So that was a bet. Now, they have the good electrochemistry, they have this good mechanical property, but probably the mobility of lithium is an issue. So you want to screen all kinds of different compounds, and that's just an example that you can use high throughput calculations to go through like the ICSD library and say, well, what's the binding energy of lithium and of these compounds? But coming back to my early statements about modeling allows you to imagine. Imagine we could simply replace lithium by, say, calcium. Lithium is not all that abundant, and you probably followed the discussion right now in Serbia, where Rio Tinto wants to build up lithium mining, and environmentalists say, no, they will destroy the environment. Well, you cannot have it both ways. I mean, you cannot have cell phones without lithium, but maybe you can. So calcium actually is a serious option. Maybe sodium also, but the calcium would be nice because you have already 2 plus charges rather than 1. Now the other, geopolitical problem is cobalt. When you look at the cobalt mining in Africa, it's just horrendous. Yeah? And wouldn't it be nice to replace cobalt by something that's abundant like iron? Well, iron 2, iron 3, or even iron 1 iron 3 would have the redox capability. And there are lithium iron phosphate batteries. I think there's a lot of opportunity to be environmentally responsible, work with materials that are common, like calcium and iron, and yet get good performance. But moving on to yet another field, I have to admit that in our company, sailing has a certain connotation. Because in the early days when we started the company, well, we didn't have much money, so bringing everybody and paying for hotels was expensive. So we said it's much cheaper if we hire a boat, and since we are spread out over the different countries, so this is a good team building. So when we started the company, that was in Le Mans, in France, not too far away from Brittany, after all. So we rented boats, and one of my colleagues, Walter, is a very good skipper, and so we rented a boat, and hence the connection with sailing. And of course, the real reason we hired Leonid is that he has a skipper patent, right? But he also does some good work. By the way, this is a boat that's Armel Lecléache. He won the Vendée Globe a couple of years ago. And with these incredible machines, which are really a triumph of material science. I mean, you have these sails that are, Kevlar fibers or carbon fiber reinforced, and you have the hull, which are high-performance materials. And in particular, you have these foils and so forth. So, I mean, a lot of high-tech in there. So what can we do actually in modeling with in this polymer area? We have colleagues in our company, especially Dave Rigby, who are really experts in polymers. So, of course, when you tell him, can you calculate a glass transition temperature? He says, oh, no, you cannot do that because when you do an experiment, you are cooling down over seconds or longer or minutes. And when you do a simulation, you're going down in a few nanoseconds. So it cannot work. But I would admit, if you make comparisons, then relative changes are okay. And it seems empirically, in a certain protocol, you always get 50 degrees above what's experimented. So how do you measure then computationally a glass transition temperature? Now, theoretically, you would take a polymer that is high temperature, you track the volume as a function of temperature. And what you should see is, if you cool it down, that at the glass transition temperature, there's a kink. Well, you tell me where the kink is. I mean, you can build a monomer, you can make the polymer, you can pack it, you have a very good force field, so you run all that. But now, more is different. You run this 100 times and get good statistics and then make a fit. And then you get a very nice signal. So that's one property. But here's another one, and that's more related to composite materials. Now, you have, as you might know, epoxy materials. You have a resin. This is an epoxy resin. Here's this epoxy group. You have a cross-linker, typically amines. Then if you have, for example, a glass fiber, what you want is, of course, a good bonding between the resin and the inorganic phase. And what's being used is, you say, well, chemists are very clever. They say, well, let's put in a linker, kind of a primer, that on the one hand looks like SiO2, so if these SiO groups, and on the other side it's an amine that will cross-link. So question, how much primer should you put on the surface to get maximum performance? Well, you would say if one is good, two must be better, so just fill it up and off you go. Well, that's what Dave did. So you create a model of the surface. You put in the primer. You then polymerize the resin. and you end up with this kind of model. And then, in order to measure the bonding strength, you calculate the mechanical properties and look at the elastic coefficient C33. That is an indicator. And what do you find? Well, the C33 is 7.2 gigapascal if you have no primer. Goes up, and goes down. Aha! So there's a sweet spot. So you tell the engineer an intermediate coverage of the primer is the optimal. And then you can go in and say, well, what is it mechanically and atomistically that gives you that unexpected behavior? So here's an example of in composite materials. Again, one of the challenges, I remember a discussion with an engineer from Airbus, and so she's working on composite materials, and asked, well, do you have an ability to predict the lifetime, how it's going to age? And she basically said, no, I mean, we just do experiments. And again, in the aerospace industry, it takes like 10, 20 years to get material in the process certified. Here's my last example, CO2 capture. And that's a collaboration with a French company formerly known as Total, now known as Total Energy. They also changed the logo, which probably they should have spent the money on modeling rather than changing the logo. It's another story. In any event, a very nice collaboration. And the problem was the following. When you have natural gas, it contains CO2 that you want to remove. It also contains H2S, and that's another story, but it's about the CO2. So the question is, the current process is you have an aqueous solution of an amine, and then the aqueous solution, you basically bubble the gas through this aqueous phase. You get an exchange, and you capture the CO2, and then afterwards you take the liquid phase with the CO2 and you regenerate. So, and that costs you energy. So you want to balance the absorption and the reactivity in the first part with the energy that's needed to regenerate, that you want to minimize. So how does CO2 absorb in an aqueous solution of an amine, and can we model that? Here I worked with our colleague Xavier Rosanska, and I can tell you it was tough. Because at first thought, oh well, when you have CO2, you first get a physisorption, you calculate the Henry constant from perhaps molecular dynamics, and then there must be a reaction between the CO2 and the water and the amine, forming HCO3 minus, and that will be the form in which the CO2 is ultimately dissolved in an aqueous solution. Well, you try to model that with quantum mechanics, and you find out you just don't have the accuracy. So we scratched our head, and then we said, well, maybe the mechanism is such that the amine, when you put it in water, reacts with water, forms OH minus, and then it's actually the reaction of CO2 with the OH minus forming this one here. This reaction will have a certain barrier, and the barrier will change if the free energy of this part in solution versus this part changes. How do you calculate the free energy difference? Where solvation effects play a role, you get a very, very good force field, and you run very long molecular dynamic simulations to get all the cooperative effects, and lo and behold, it worked. That took us about over a year to find out. So at the end of the day, we found out that by a model that connects the reaction of the absorption with kind of the free energy barrier of the reaction of CO2 with OH minus in a solution that contains the amine. And of course, you have the concentration of the OH minus, which is related to the basicity of the amine, and of course the concentration of the CO2. And then what we used, well, calculating with molecular dynamics a barrier, a transition state is not obvious, but there's this wonderful kind of relationship that Polanyi Evans says that, well, if you have a reaction going from this part to that part, namely from solvated of these two species to that one here, if you change the relative energy, then you also change the barrier. So all you need to do is you calibrate on, for example, pure water, where you know the experimental barrier, and then use Polanyi Evans, and then it turns out we got an accuracy of 0.2 kilojoules per mole. That's what's needed to get this correlation. So the bottom line is that that was published, and Svenja can talk about this together with Frédéric Demillière from Total Energy. And we're using this now to improve these materials. Now, I should say that now what's being done is that we use modeling to predict new candidates. There's a collaboration with a group in Strasbourg that uses machine learning to build correlation models, because we can generate a lot of systematic data. And then a collaboration with of Total with the École des Mines in Paris who do the experiments, and so that's happening. But clearly, the simulation is now guiding the choice of these amine solutions. And it has to be said that chemistry can be, especially industrial chemistry, can be extremely subtle. And it reminds me of a statement made by Tom Holgren from Merck shop in Dome way back when. He was a modeler in the 1980s. He said, you know, in a drug company, the difference between a blockbuster drug and a disaster is 1 kilocalorie of binding energy. So nature and also chemical reactions can be very, very subtle. And that's a tremendous challenge for modeling. So I want to summarize here. So we started out with some philosophical, humanistic considerations of why we do modeling. Well, I think one of the reasons is also it's just fun. I mean, it's just great if you build a model and it actually can predict something, and even if it's useful, it's even better. Yeah? But it enables understanding, predictions, innovation, and then I talked about the challenges, especially related to primary energy, and this is really the challenge of your generation and the future generations. I think our generation left you with an economy that is much too wasteful, much too generous with our natural resources. So we need to be very, very clever to maintain the high level of quality of life that we have, with the ability that we can jump in a plane and fly to the other side of the world at an affordable price. It's wonderful, but how do we do this in a sustainable way? We need to be very creative, and I think modeling more and more will play a very important role. And I've tried to illustrate this in specific examples, like these zirconium alloys, where an effort is underway to create so-called accident-tolerant fuel systems. So, for example, you can replace zirconium with silicon carbide, namely silicon carbide fibers embedded in amorphous silicon carbide, one possibility. Or you can coat the zirconium with, for example, chromium, or with some other alloys, and lots of opportunities here. Then we talked about electronics. How can we make our devices less power hungry, smaller, better control of the effective work function, better control of the ohmic contacts. Batteries, well, improve safety. I think not only performance, but also safety. Polymers, I mean, yes, they will play an increasing role and for all kinds of structural materials, especially as we build very lightweight structures, first in the aerospace industry. I mean, for example, you take an Airbus 350 or the Dreamliner from Boeing. I mean, they're basically plastic. Let's not put it this way, but they're polymers, high-performance composite polymers. And the same for cars. So there are lots of opportunities. And CO2 capture. In a sense, if we could capture the CO2 out of air, and I understand in Switzerland there's a company that takes CO2 out of the air and puts it back in the bottles, right? And makes carbonated drinks. If we have good capture technologies, maybe we just take it out of the air, or actually where the CO2 ends is really in the water. In fact, the Naval Research Lab has developed a prototype where they use the power of, like, if an aircraft carrier that has a power plant, a nuclear power plant on site. So if it's sitting there, you run the nuclear reactor, have free energy, so to speak. What do you do? Well, you take the CO2 out of the water, you use the water to create hydrogen, and then you basically create from hydrogen and from CO2 with nice chemistry, you create fuel right there. So having access to cheap, sustainable primary energy is key to so many technologies. And hence I focused on this primary energy so much. So I've illustrated that also for the CO2 capture. So if you look into the future, I would say that we are clearly entering a golden age of computational material science. We have solid theories and powerful algorithms, and here in particular, CECAM has played a key role. Well, the division of people like Carl Moser and all the people who've worked. Well, let's look deeply at what are the algorithms, what is the physics behind materials modeling, molecular modeling, how can we improve that? And that's fundamental. We have, there's still a lot to be done, but we have tremendous capabilities. We have sophisticated software, very complex, comprehensive environments that allows you to go from ab initio calculations, you're creating on-the-fly machine learning potentials, use them in molecular dynamics, you coarse graining, and you feed them into mechanical, chemomechanical, and phase field models. So these environments are there, and we have unprecedented compute power. And no other human-created tool has seen in the last few decades, in such a short period of time, such a development. So it's unprecedented. And think about it, the material that we're using fundamentally for the semiconductor is still silicon. It has not changed in the 50 years or so, but we've learned to make it better, better, better. And that's what industry is all about. It's this persistence, this industrious activity that you really keep at it. I mean, when you look at really successful companies worldwide, take, for example, in the car industry, we have good relation with good friends at Toyota. I mean, they're really, when you talk with the engineers, that they're almost obsessed by saying, I want to make things better and better and better and safer and safer and safer. And the same with our friends at BMW, and the same with our friends at Total. Well, we want to make our processes better and better. And so don't expect that computational material science will just completely revolutionize things. No. I mean, there may be some disruptive steps, but then followed by long periods of systematic improvement. But we need higher accuracy, and I've shown this for this chemistry example of CO2 absorption. If you would tell a quantum chemist, please tell me, predict the absorption of CO2 in water, just these two components, and from purely ab initio, would not be able to do that with accuracy. You would get an order of magnitude. I mean, because our quantum chemistry, transition states, if you're down into the kilojoules per mole, you're lucky. Maybe it's more like a 5-10 kilojoule absolute accuracy, maybe relative accuracy better. So that means going really back to the fundamental many-body theory. That's why we need work on the fundamental level. We need tools to simulate complex systems. Nature, they're always industrial problems, are always complex, multi-scale problems. And also, yes, we'll use machine learning and data-driven and all that, but let's be real. This will not take away the human effort to really go in and sit down, think very hard, learn about what's really behind. There is effort. It will not just fall into our laps with machine learning magic. Machine learning will be quite nice for optimization. If you have good data sets, it will have its role, but it doesn't take away the deep fundamental understanding. Think, for example, if Newton would use a machine learning approach, he would have measured millions of pieces falling down, and what would he have discovered? Well, he would have a neural network that would predict everything, except not Newton's law. So I think we need to be very careful that we not get carried away with this AI euphoria. It will have a role, it's wonderful. And by the way, one of our customers is called Facebook. Sorry about that. But they have FAIR, Facebook Artificial Intelligence Research Lab. And they're using their technologies of pattern recognition and so forth to work on batteries, battery problems together with Carnegie Mellon. So it will have its role, but nevertheless, I think theoretical, mechanistic understanding cannot be replaced. It always will play a role. And especially when we look at how do we span the time scales of 15 orders of magnitude? Because it's not the length scale that is getting us, it's the time scale. Or another way saying it, it's the configurational complexity that we have in a system. And that's the beauty of nature, that it has all this configurational richness, and yet at some points, kind of bifurcation points where a small difference can lead you into this phase or that phase. I mean, nature is just fabulous. Most importantly, we need you, young scientists who are really fascinated by material science, by the capabilities of materials modeling, and who will dedicate their lives and professional careers to this field. And so here's the guideline. Seymour Cray, when he worked, just before he founded Cray Research, he worked for Control Data System, and he was asked to write a business plan. He came back, and that has 3 words: proceed with confidence. So let me stop here.
Great for this very engaging presentation. Now we have some time for questions on the presentation. Yes, Michele?
So thanks a lot. It's very, you're really covering many different branches of material science. So one thing that sort of stands out from the examples that you gave is that I would say almost all of those, so you were really after. So there was a technological problem, and you were after a mechanistic understanding of that technological problem, more, at least that was the impression that I had, more than a quantitative, computing directly the figure of merit or whatever is the, so this is also very much similar to what we do in academic research. Is often more about the mechanism than precise number, which we don't have that precise number usually. So is this it's just anecdotal, or it's something that you find regularly throughout the vast majority of the projects?
That's a good point. Why is it that all these examples aim at an understanding rather than say, well, here's a system, predict me that situation when I change this or that or the other. And I think in industry, understanding has a higher value than just predicting a particular property. Because, for example, this business with the work function lowering or work function increase. Well, if you don't understand what's driving it, you may be able to predict something, but it's really the understanding which is the key to innovation. And quite often what you do is, in industry, you have a lot of experimental evidence and also anecdotal evidence and empirical facts. And you want to get an understanding. And yes, indeed, you need the quantitative aspect as well. For example, this case with the epoxy bonding on the silica surface. There it was quantitative to say, well, go up to 25 or 50% or 25%, but not higher. But that comes later after you establish a kind of the conceptual framework. And I think also quite often, and in our company, we do quite a bit of contract research, kind of feeding our project and product development. And quite often, after these projects, the customers come to us and says, well, actually, we've never thought about our problem in this way. And so it's this understanding which probably has a higher value than saying, well, the answer is 42.
But then, it's sort of to be provocative, but one of your final points was that we need more accuracy, right? But if we are mostly after qualitative mechanistic understanding, we may not need much more accuracy.
That's a good point, and it really depends. Yeah? So if you're like in this CO2 absorption, if the whole story hinges on a few kilojoules, you need that accuracy. Otherwise, you're just flapping your gums. It's what you often want to do is you start with the high-level model and ask, and I think Bill also keeps pointing that out all the time, you basically look at what are the key mechanisms, the key phenomena, and how accurate do you need to know them to make a decision. And it could be that, just yes or no is enough, or you need it down to better than a kilojoule. It depends. So you still need the accuracy, otherwise you may be just lost. So you need both, yeah. Okay. But very good question.
I don't know if are there questions from. So what is then? I mean, building a bit on this, what's your experience, or how do you normally work with companies? Because I mean, it looks that at the end you end up taking a request and really going into it. Sometimes you say it took like a year. Mm-hmm. So is that also a question of the timeline in this interaction with companies? How far or how fast they expect the solution, or how you have this ongoing collaboration with them?
It depends, but I would say it ranges from a few months to a few years. That's also typically when you have industrial R&D projects. That's the horizon. Okay. For example, this CO2 capture, when it's ongoing, I think probably now they're changing the supplies of the gas and say, well, we need to adapt it to these conditions here. So it's quite often ongoing, actually.
I have an understanding question with the silicon primer polymer section. So did you develop an intuition for why you get this peak? Is it like as you come to, so I guess if you say let's go to full 100% coverage, you've essentially reset and almost restarted. So at 50%, have you made like a fractured layer that itself breaks off the surface instead of the primer becomes part of the substrate and breaks off instead of acting as a primer?
To be honest, we haven't followed up as we should have. But actually, when you look at what we calculated, or what Dave calculated, was just the elastic coefficient, so in the elastic regime. And so it's basically just the bonding between, I suspect it's some sort of entanglement, that if you have too much primer, then the interface between the primer and the polymer may be the weak spot. But there's room for further research. Yeah, very good question. Yeah.
So yeah, I was wondering if you could comment. So it's just more general question. If you could comment on what you think will be the future of materials modeling in industrial research. In particular, I was wondering, so do you think the companies are starting to realize the power of modeling to drive innovation? Are they starting to employ it, or do you think it's still a slow process that will still take some time?
Well, the answer is yes, especially large companies have been doing materials modeling since decades. Japan has been a pioneer in that field. For example, Sumitomo Chemical had a modeling group since 30 years or so. BASF in Germany, more on the quantum chemistry side, and also polymer side, also 20, 30 years. So the large companies have established modeling groups. And the field is growing, and I think it's, the progress kind of scales with the awareness of management, and I think it has accelerated simply because now a management layer is in place that has already been educated with these tools. So 20 years ago, the managers had no clue of what modeling could do and were skeptic. So that is changing. So I would say that there's a steady increase, and I mean, companies, R&D is an expense for a company. So you need to be very careful how you invest your money, how you spend money. And the more modeling becomes an integral part of the R&D landscape, the more this will grow. I think there's a steady growth. I mean, I don't see step functions or anything, but I see a steady growth. And quite often we're being asked by companies to say, yeah, I mean, wonderful technology. Can you recommend someone? We want to hire a modeler. So yes, and I think there will be a market and a need for more and more modelers. And that's kind of then autocatalytic, yeah, because that will mean that we'll have more demand. That means more supply on the software side, better software that will generate more interest in academia for careers, and so it will accelerate. But let's be realistic. What can and cannot be done? It will be very dangerous, and that happened about 25 years ago. It was oversold, and literally at the GE, people were fired. Because they were promising things that they couldn't deliver, and out. So that we need to be very, very careful what can be done and what cannot be done. But I think it's the writing is on the wall that this is a technology and a part of R&D that's not going to go away. In the contrary, I mean, it will become more and more problem. And also, I may have sounded a little bit negative about AI and machine learning and so forth. It will have its role, but it will not replace this mechanistic work. You need to think at the end of the day, you need to understand your materials, and you need to understand how your modeling is being done.
Sarah, I think there is a question.
We have two questions from the people who are following us on Zoom. The first one is from Nicola Natali, who is well known to this community and present in spirit even when he cannot be present in person. So the question, he starts by thanking you for the inspiring talk. And then you did mention the unprecedented development model of computational science. I often call it the 100% return every 16 months. In this, do you feel that our policymakers setting the research agendas have really figured out the correct investment model, for example, supporting hardware development versus software development, or even the career paths that we need?
Very good question. So if you're watching, Nicola, buongiorno. Are we making the right policy investments given, and I think that could also be directed at Brussels. Where's the real bottleneck? And I think the real bottleneck ultimately is people and education. So that should be there should be a lot of investment on that side. In terms of software, well, maybe we come back in a discussion. I think Europe is in a fairly unique position to create innovative software and to turn this into real business. We've seen this in the finite element business. I mean, the finite element business, multi-billion euro or Swiss franc, whatever your favorite currency might be. That's a big business. I mean, what are we going to export to the world to keep our standard in Europe? Well, the Swiss chocolate is nice, but Swiss cheese. But I think we need technology and information technology in the form of software and know-how will be one of the export factors. That's why I think we should actually invest. Yeah? Hardware development. What's happening right now? I mean, it's still, in terms of processors, it's the US. It's a company like NVIDIA or Intel, AMD driving that. Europe, unfortunately, has lost the pedals in this respect in the last 30 years. Although there's always a possibility to innovate and turn things around. But yes, overall, I would say the investment should go into people. I hope that answers your question, Nicola.
You will complain otherwise. So,
I
go with the
really
second
think so.
question.
So second question from Otello Maria Roscioli. This is a two-part question. How hard is it to sell materials modeling services to manufacturers? And how willing is a customer to share its secret sauce for modeling?
Well, of course, companies want to deal with companies because then they know someone that they can sue. Right? That other one is on the line. So basically, what happens quite often, I should say that in our company, the contract research is a small part of the entire system. So most of the time, you sell the software, you sell the basic know-how, how to use the software, and then for the really important project, they use it in-house and stay quiet. On the other hand, for the more fundamental question, for example, this business with both the Texas Instruments story and the CO2 story, companies are not adverse actually at the end publishing that. Well, it could also be published in the form of a patent. So basically, when our company does this kind of contract research, the first step is a non-disclosure agreement. And they tell you quite openly. Not always. They also sometimes probing you. They say, well, they tell you half the story and say, well, show me that you know the other, can find the other side. But most often, it's very open. And those are long-lasting relationships. For example, with Toyota, I mean, we've worked with them for the last 20 years or so. So I think at the end of the day, it's a matter of trust. And especially, as I said, companies want to work with companies because then there's a legal kind of balance there. And that doesn't exclude the involvement of universities, because there may be kind of a generic, longer-term fundamental aspect that's best handled by a university group. So, for example, this business with the high-key dielectrics, that involves the University of Texas in Dallas for some of the experimental work. So, usually, I mean, this confidentiality, yes, it's an issue, but it's usually not a showstopper.
Okay, thank you very much. I think it's a good moment to stop. I'm sure there will be more questions ongoing, but maybe we can now move to the second half of this more informal discussion. Yeah, so thank you. I'll set the floor for you with Bill.
So, okay.
Better view from the camera. Yeah.
Grab something.
Yes.
Drink here.
Have a drink.
Yeah.
Yeah, thank you very much, Erich.
Talk about CO2, right?
I don't know if we'll solve the problems by making Perrier, but we can try. I really like your title because between the fascination and the industrial value, because I think we have an infinite number of problems we could try to spend our time solving, right? And they're all interesting. But which ones are valuable? Which ones should we spend our time with? And often you have to talk with people in the industry to figure out, out of all this spectrum, some are fundamentally, there's certain things that are fundamentally interesting, but there's lots of really interesting industrial problems that are equally as interesting as more fundamental, or I shouldn't say more fundamental, but other problems. But if you solve them and you provide insight, then they have real value. So I think it's that twist and the paying attention to what's relevant. So I had a bunch, I think actually it was very nice questions people asked, which covered some of the topics we'd already discussed, which helps because I think there's several things about doing things live, and one of them is the apparel. And the apparel will follow, and people will start to demand the apparel. So I want to turn back the clock a little bit to start out with, and just way back, not for us, but you did some seminal work in electronic structure theory when you were working with Art Freeman in the early 80s and a little bit earlier than that. Could you tell us a little bit about that and what it meant for electronic structure moving forward at that time? Because now we take a lot of this stuff for granted.
It's a good question. It goes back, I did my first band structure calculation probably 1972 or maybe 71. That was for my master's. And I was working in Vienna at the Technische Hochschule, as it was called at the time. Now it's Technische University. Maybe a little bit of background. Why did this group in Vienna do electronic structure calculations? It goes back to people like Hans Nowotny, who had connections with Plancy. Plancy is a company that makes specialty materials. One of these compounds that they make is like titanium carbide, titanium nitride, vanadium, tungsten carbide, and so forth. And the question, was asked very early on, titanium carbide, isn't it strange? You have a structure that has a sodium chloride structure, it's a salt, like an ionic structure. It has the hardness of a covalent material, and it's an electric conductor. How come? And the answer must be in the electronic structure. So that was kind of the beginning. So then there was a relationship between MIT, this later group, and Vienna. And Vienna got a very early form of the so-called APW program. Now, when you think about it, so this was in the 60s, really. So there were people like Dolph Neckel, who was my thesis advisor, Peter Rastel, Peter Weinberger, and Karl-Heinz Schwarz, who was a postdoc with Slater in Florida. And so there was a connection. And the first step was to turn a non-self-consistent muffin tin program, APW, into a self-consistent. There were people like Peter Herzig, who sadly passed away, very, very good, careful theoretician, Renate Eibler, and others. And so I kind of inherited and got into that group. Now, my PhD thesis was the following, was scandium phosphide. And Neckel said to me, you know, it's kind of strange, scandium nitride, scandium phosphide, they are actually semiconductors. You have an optical gap, but when you do these band structure calculations, they seem to be a metal. Can you fix that? So I did my first band structure calculations on scandium phosphide with the APW method. And that was done at the Supercomputer Center of the University of Vienna, which was an IBM 360, not to be confused with the Workstation 360. So that was basically the spin-off from the Apollo program. That was the biggest computer. It was already transistor-based. Had a main memory. Now the memory was still magnetic core, so these little donuts, with I think 40 kilobits. We got access to this supercomputer in the graveyard shifts. That means on weekends between late evening till the Sunday morning or so. If you're lucky, you could do in one night 1 or 2 SCF steps. Yeah. So that was the beginning. Yeah. Now, when I look back, what is amazing, how little actually the basic algorithm has changed, the fundamental physics. I mean, the APW idea of Slater, 1937, you have electrons around the nucleus. They're like atoms, so you describe them as spherical harmonics. In between, you just don't know what it is. For expansion, classical quantum mechanical tools, you match the value and not even the derivative. Yeah? That's the APW method. Already at that time, so that was the starting point. So that's how I got into this business. And then I was reading Slater's book. I was reading also Pines and Moe, and didn't understand a word. As a poor chemist, I mean, how can you understand this kind of many-body theory? But I did understand Slater's work, and I said, what he actually did for the X-alpha method is he took the densities and the wave function, the densities, and fitted that. So why don't we do this also for the wave functions and create an effective potential for each wave function? And this way I was able to simulate Hartree-Fock. Yeah? And then I said, well, great. If I use the true Hartree-Fock, I get a big band gap. And if I do what was not yet called the DFT, it was called just the exchange correlation potential. It was the Gaspar-Kohn charm, which is standard LDA now. There you don't have a gap. So just said to my friend Raimund Podlutsky, well, why don't we mix it? That's not serious. I cannot do that. Yeah. That's not good physics. Yeah. So that was my PhD thesis. Yeah.
Okay, thank you.
And then, of course, after my PhD, I went to Art Freeman, and there Dale Kölling and Gunnar Ardman had developed the LAPW method, and Henry Krakauer, now caller for William and Mary, he had come from, what was it, Mary Cooper, I think, knew about the surfaces and how to deal with surfaces. That's what we developed the the surface FLAPW method. In particular, worked with Mike Weinert, a brilliant computational physicist, and we picked up this idea from Don Hammond about how to solve Poisson's equation, and so that became then the FLAPW method. And
Don
I can
Hammond
tell
was at Bell Labs.
it was at
right?
Bell Labs, but he had the idea.
Industrial labs coming up with.
Coming with the idea, and then when we implemented that, Don said, "Oh, well, I'm really glad to see this implemented and working." So it was really many people. And Art Freeman created a group where all these came together, and Art Freeman got us access to a Cray. Well,
that leads me to the next question, because you worked at Cray
yes.
for a while afterwards, and you told me, but I never got detail about that it was a very interesting environment that had been created.
Oh yes.
And your experience was unique. So could you a little bit of detail about that, about
yes.
what was going on at Cray?
I learned a lot about business and about good companies. Now, Cray Research, I joined in 1985 because they were looking for someone who could help developing the market in chemistry, material science, and pharmaceuticals. And they knew that the access to this market is via applications, via software, via showing what can be done on a supercomputer, what couldn't be done otherwise. And so that was in Minnesota. What is striking about Cray was like a big family, very, very supportive, and everybody in the company knew what the mission of the company was, namely building the world's fastest computer. That was the mission.
Just a small goal.
Such a small goal.
But with confidence.
With confidence. That was Seymour Cray. Now, he was quite a character, actually. But very, very, I remember an episode where it was a kind of an event. We both went windsurfing. He was a good windsurfer, actually. And on the way out there was a gardener planting little plants in a certain distance. Seymour Cray stopped, turned on to me and said, "Well, how does he know which distance to use between these plants?" What it tells me is that Seymour was interested in any kind of detail. He was curious. Mm-hmm. But this climate, and then the CEO, that was John Rollwagen, he created also and fostered this kind of experience in the company that, you really want this teamwork, you want everybody to understand what you're after, and you support each other. So it was, and also I think, and maybe it's perhaps a little bit too optimistic statement, but when you think about really good companies, they don't aim for making the maximum profit financially. No, that's the result. What they should aim for, and what a good company aims for, is making the best product of its kind. And then, of course, if you do the right thing, it is valuable, you get compensated for that. And Cray had a good budget at the time. So that was, and I stayed there 7 years, and I learned a lot about also how companies are organized, what makes a company really work, and I think ultimately the focus on the customer.
So that leads into the next question, because the next step was, forming a software startup, essentially, right? You learned some things being at Cray, which was kind of intermediate size. But so what were the challenges when you started getting into that? Because many people may, some of these our audience may be thinking of startups, and maybe not Facebook and Google, but
well, who knows?
Smaller scale, and maybe that's where they'll start. And so, what were the challenges, or what was unexpected that turned out to be absolutely crucial that you never would have thought of ahead of time?
Well, let me
if anything.
Let me back up for a second. So what happened when I was at Cray? one of my first assignments at Cray was the evaluation of a proposal by this little startup company called Biosim Technologies in San Diego. And what did they propose? They proposed, believe it or not, to develop force fields for proteins. And so they formed what's called a potential energy function consortium. So that was on my desk, and my boss said, well, Erich, what do you think, should we join? And I looked at it and said, well, kind of interesting. And they wanted like $30,000 per year. I said, we don't want to pay cash. We give them in-kind computing time. Because the idea was of this consortium started by Arne Hegel and Dominic Kay, to use ab initio calculations on small molecular fragments to calibrate force fields, which actually became later on a force field that was being used for these amine solutions. I mean, that's the history. So that's where it started. And then I became a very good friend of the president of that company, the startup company, Dave Klipstein. And I think it was the model of Dave Klipstein that helped me and my former colleagues at Biosim to think about starting our company. What actually triggered it, that Biosim Technology, which was a very science-oriented company, was then through some, various events merged with another company, and that didn't really work out. And it was Paul Sachs, John Harris, by the way, the John Harris from the Harris Functional, whom we hired for a consortium, and myself, we stood there and said, I think we can do better. Really, the guiding line was actually Dave Klipstein's model. And so, what were the key events there? Well, first of all, you need quite a bit of courage.
Confidence. Confidence.
Confidence, yeah.
And courage, yes.
And willingness to take a risk, yeah. And I mean, that was shared. I mean, it was, as I said, Paul Sachs, then John, and then also Jürgen Sticht and myself, and so that got us going. And what helped, I think, at the beginning was through my previous work at Cray, I had quite a few contacts with industry. There was a certain confidence that yes, what we're doing had a future, and we found very early on customers, including like Clint Geller at NNL, but also like Norsk Hydro and others who said, well, and also Alain Lemioté, he was the director of an engineering school in France. He said, well, if you start a company, I can provide you with an infrastructure. So then, well, we started with confidence, and Paul had written an initial version of Medea, and then we negotiated a deal with Jürgen Hafner to got VASP as part of the environment, and then things started to develop.
Okay. So things you didn't expect that you encountered? Maybe not.
It of course takes much longer than you think. That's so. In principle,
You're talking to a lot of PhD students. They know that. The professor says, "Come on, do this," and a couple of years later, it maybe gets done.
Well, the rule is make a first estimate, double it, and go to the next order of magnitude.
Okay. All right, well,
so it took longer, and so I think a key was really getting the support of customers, because at the end of the day, well, you need to bring in money.
yeah.
And also, of course, at the beginning, we tightened our belts and just made sure that we wouldn't sink. Yeah?
Or swim as fast as you could. So you've been running this business for 30 years now, maybe.
No, over 20 years.
Yeah, okay, not
I mean,
quite.
technically what happened
it
is
depends
that,
on the...
so the American company, which initially was called Psycho, a science company, and if you read look at the file names, there's a .sci that goes back, and then we started the European company, and also that may be very, very surprising. Starting a company in the US is formally very easy, but actually in practice very complicated because then getting health insurance and all that is very complicated. Whereas when we started the French company in Le Mans, and it always surprises people, it was actually quite easy and very well structured. We are guided by the Chamber of Commerce of Le Mans, and they guided us. So what you need is a good lawyer who knows how to set up the statutes and guides you through the legal procedures and the formalities. And then a good accountant who helps you with setting up the financial environment and so forth. And perhaps one aspect that may sound surprising to you. The most difficult part is not getting good scientists and engineers. The most difficult part is getting good, we can call it salespeople, but in reality, those are the people, account managers sometimes they're called, but they're really technology managers. And what turns out you need, and we have in our company, they are very accomplished scientists, like Steve Mumby, a very accomplished polymer scientist, worked at Bell Labs and IBM, or Brian Tron worked in catalysis, a PhD in catalysis. So they know the science, but they also have these personal skills of finding out, how do you develop a contact? How do you know in a company with whom should to talk? What is your obstacle? What is your competition doing? How do you position that? How to orchestrate a sale? It's a long process. So don't expect that if you have a fantastic product, you put it out there on the website and wait for the phone to ring. It won't.
It's not the science, not the technology. There's a whole...
it's the whole communication.
Yeah.
Now it's called marketing, but really it is understanding what is the market need, developing these contacts, building these relationships. And then there's one thing in our business, because we're dealing mostly with very sophisticated engineers. They're skeptical. It takes a long time to convince them. But once you have them as a customer, the retention is over 90% or so. And if you lose customers because there's a merger or a restructuring or something like that. So there's a lot of inertia. So the initial barrier is high, but once you're in, and you really need to work hard to lose them.
I'm sure you work hard to keep them too.
Yes. And that's the other thing. We have in our company a very, very good support team. They're high quality scientists who like to work with customers, help them with solving their problems.
But I suppose then going back, you had benefited early on from your experience and interactions at Cray then in terms of building some contacts.
Yep.
So you didn't start in your basement hoping somebody might need this.
Yep.
You kind of had contacts already, which helped maybe launch you a little
faster. Absolutely, including contacts in Japan. Yeah. Japan became very early on a very important market, like Sumitomo Chemical and so forth.
So this was addressed a little bit, but how do you deal with customer needs, or maybe I shouldn't say needs, but desires vis-a-vis computational science? Often the companies want the results.
Mm-hmm.
We discussed, or you, in response to answers, you talked about, there's insight and mechanisms and not necessarily specific numbers. But sometimes they want you to give them the answer. They want to solve, the problem. And the reality is computations, we know, have limitations, right? DFT even, right? Much less force fields, much less time and length scales. So how does one manage sort of that, the expectations and with respect to the deliverables? Of course, if you give them something they really didn't understand is really important, then I think you're in good shape. But you have to get over that barrier, maybe. So how do you manage that?
I would say that two types of customers. Customers who buy the software who have already the in-house knowledge to know exactly what they want to do, and they look at the functionality, and so then the support is more, yes, you can really do what you imagine. And so they can be called, or this function, translator, meaning you want an interface between the end user, that's often a product engineer, or it's not even it could be an engineer responsible for something goes wrong and they need it to be fixed. And so they go internally to the R&D department. If it's an easy problem, the R&D department in-house solves it. If it's a hard problem, they come to us. And then it's really a lot of communication and a lot of listening. And I think, who was that actually? Maybe Adrian Sutton made this statement like, when you work with an industrial customer, three things to remember. Number one, shut up. Number two, listen very carefully. And number three, be prepared something that you've never done before. And so don't come in and say, well, look, I have this wonderful thing here. That's not the approach. I mean, you want to understand, to listen. And this listening skill, that's a skill of the account manager, of the support team. And then the first level is that, establish a level of trust. Then it's a process.
And the listening, and then enables you to think, what is the problem, right? What underneath the things that they're telling you?
Yeah.
What are the science problems that we could apply computational methods to try to solve? Maybe your salesmen or marketing people deal with this, but there are problems we can't solve. Mm-hmm. So are you guys not happy, but willing to have companies and say, well, we can't really help you solve your problem?
Yeah, it happens. And companies, they honor that and appreciate that. If you say,
I think
honestly,
so, right?
Either it cannot be done, nobody can do it, or we cannot do it. Right. It occasionally even happens that you say, no, but we cannot do that, but company X maybe have it. Yeah. When you go into a store and the store doesn't have what you're looking for, but they say, well, maybe there's this other store, they may have it. You say, well, thank you, that's very nice of you, and you probably come back to the first store next time.
Yeah. That's part of the developing, maybe the trust, right?
Yeah.
Rather than saying, oh, actually, we're not sure we know how to solve it, but let's take the contract and try to deliver.
Yeah.
That seems very risky.
That's risky.
Because you ruined it.
Sometimes
this happens.
It happens, and managing the expectations is part of the deal. Yeah. And one has to be prepared that the customer says, well, you didn't answer. But of all the projects that we did over the last 20 years, I've never had a project that was a complete failure. At best, or at worst in that sense, it was a learning experience for both sides. Mm-hmm. Okay, we've learned something. Probably didn't get exactly what we set out for, but that's research. If you know the answer, it's no longer research.
So let me just ask one more question, and we'll take a few other questions from the audience. So materials design has an interesting mode of operation for a worldwide staff. Maybe you could tell people as a way in. I don't even. Where do you live?
In Zurich.
You live in Zurich, yes, and Erich lives in Versailles and Bretagne, and the company address is in San Diego. So maybe just say a little bit about and what the benefits are, or challenges maybe?
Benefits and necessity. I mean, on the one hand, it was an opportunity because in the information technology business, the manufacturing can be delocalized. Yeah? I mean, you can development sitting here on a desk in Zurich and collaborating with someone sitting in San Diego or sitting in Montrouge in Paris. So that's possible. And so I think from a purely legal structure, it is a multinational company. So there's an American company, Materials Design Incorporated, a Delaware corporation. There's a European company, which is Materials Design SARL, the French company, with employees in Europe, the American company with employees in the US. And so from that point of view, from a business structural point of view, it's a classical multinational company. In terms of how we work together.
Classical, except there's how many employees? 25 or something?
Well, we're over 30. Yeah.
30, okay.
Yeah.
So not your usual multinational, ExxonMobil. Or
But in principle, if from an accounting tax point of view, it's...
But everybody,
so
it's not even centralized in Europe or in the US, right? So you have people.
I mean, some people say, well, are we a truly multinational company or just all over the place? But no, it works out fine. And because of our business, from the very beginning, yes, we did have, we actually started out with an office in San Diego, then had an office in Angel Fire, New Mexico, of all places, because that's where Paul Sachs wanted to live. And we started out the French company in Le Mans, then moved it to Paris. So the company has moved a little bit, but so now the US headquarters is in San Diego, and the European headquarters in Montrouge, in Paris.
But the people are working wherever they prefer.
And that's the wonderful thing about the European Union, that as a French company, you can have employees, of course, in the member states, and Switzerland has basically the same kind of relationship. So he pays, or the company pays into the Swiss social system, but he's considered as an employee of a French company.
But
and so we don't have to
living
create
in different places.
Right, and so we are not obliged to have in each country a separate legal entity, which is very nice.
And it's a quasi-virtual in terms of, I mean, everybody's interacting from their own place, and so it's the ultimate work from home kind of environment, right?
And,
but we're on the worldwide basis, which long ahead of the time it became popular.
Yeah, and so what happened with the pandemic, all that changed is we didn't travel anymore.
Yeah.
And we have daily what we call huddle, where we in each team get together and briefly go over the main topics. If they've done some follow-up, the one-to-one meetings. So we try to cultivate this information exchange. But it's true, we are missing the chat over the coffee machine.
Which I look at the clock and that reminds me of the apéro that is going to lead to other chats. So let's take a few questions from either live or virtual audience if there's anything pressing relative to the apéro. Of course, the virtual people don't care. Anything, anybody? Anything in the outer world?
Nothing for you. It's a question for me, actually.
You're in the audience.
I am in the audience, not in the outer world. Or at least I don't think so. The background from this question is because us, CECAM, but many of us here in this room are now solicited, for example, by funding institutions in the European Union to really think about not only technology transfer of what we do, but also getting in relationship of trust with industry and so on and so forth. And so, this is a new challenge also from an academic point of view. And you said before something that I thought was very interesting, which is a company likes to deal with a company. So Do you see other models of interactions that could be somewhat transferable, or do you see, for example, a company like yours as a natural in between the world of industry and the world of academia?
I think there's a role for everybody, and in an ideal world, everybody should do what they do best. What an academic-driven institution like CECAM does best is the fundamental work, and also the educational part, and the kind of very open, pre-competitive exchange and nurturing of ideas. I think it would be a mistake by funding agencies to request, oh, but you need to show a business model. Turn CECAM into CECAM Incorporated. It's a bad strategy. What I can see is that when you look at often industrial problems, there are certain aspects that can be solved with existing technologies, and there are some aspects that are really longer-term research projects. And it's not the role of our company to do long-term fundamental research. Well, we have this relationship with the VASP group, work with the group at the Sandia, the LAMPS group, work with the University of Paris on the Gibbs project. So there is this natural partitioning of tasks, longer-term fundamental research on universities and kind of non-profit research organizations, and then the integration and the solution on an industrial scale by software companies. So we need to make sure that it's balanced, and one doesn't do the job of the other.
So as you just pointed out, now keeping communication channels open between all the different actors so that everybody can contribute in the best way. We have a question here from Kevin Muzeni, and then I will. Which is, how does a young scientist get involved with teams like materials design, and when are we qualified? When?
Do you want to answer that question, Leonie?
I can only talk about a very personal experience. So I think with the discussions that we had in the beginning, it emerged that you're looking for someone who is a good scientist, but also can communicate well, and I think this was stressed a lot in the beginning. So that was quite a learning curve for me to figure that out, and so probably something that was very interesting about materials design is that there was nothing I would call a technical interview. It was basically just. Not really. That was just settled. Basically, we talk as equals, and there was a lot of communication. So I had to talk to many members and of the team, and also to members outside the research team. And it was really important that the main thing they focused on was how does this person communicate and how does this person explain very difficult scientific concepts in a good, easy manner, and engaging with the other person. So I felt that was the most important metric, but maybe that was wrong.
Yeah, so I mean, we are a growing company, and recruiting and finding the right people is one of the big challenges of any company, any organization. And typically, when you look at a candidate, you have a kind of two dimensions that you evaluate. One is the technical skills, but then there's the other dimension, the alignment, we can call it alignment with corporate values. In other words, does this person fit into the goals? Because after all, I mean, a company needs to make money. That means it needs to engage with customers and get customers to pull out the checkbook. And
and also interact with other people on the team.
And I think that's perhaps also a difference that I personally experienced when I first moved to Cray. That in academia, well, yes, there is collaboration, of course, we like each other, but fundamentally there's a lot of competition because you want to have the largest number of publications because you're aiming for an academic career and you're in competition. And in a sense, you're alone. As soon as you're in a company, your success is the success of the entire team. So there's a lot of collaboration. And that's fundamentally different. So this attitude of it's our company. And also, in our case, the owners of the company, of the shares, are the employees. So we started the company without any foreign investment. That was hard, but right from the beginning, especially John Harris, Paul and I said, if we can avoid it, we don't want venture capital, because all they want is money back as soon as possible. And we kept that as freedom. And a good friend of mine who runs a multi-billion-dollar company said to me, freedom has no price.
Just thinking about the different roles, with these two axes, CECAM, EPFL, all the other CECAM people joining from around Europe, I think that these groups ensure the quality of the technical skills across the board, right? With training and education and really doing fundamental research, which creates the innovation, the ability to think about complex problems, and we maybe can we try to work on the other axis, but and within groups and teams, but that's also a personality issue. But I think it's interesting for people to hear that it's not all about the technical skills. There's lots of people with the technical skills, and that you need people who can communicate and work with other people, not only customers, but people in the team. And that this combination is quite important.
Yeah. Right.
You don't think of that when you're a PhD student. Maybe you think, okay, I got to finish this. I got to get this paper written. I got to write this PRL. And yes, that's all important, but in the long run, there are these broader issues as well.
And I think there's another dimension. You probably see this in our company. It's really the passion for excellence. You really need to like what you're doing. Quite often I have colleagues in Germany, Volker, and we find ourselves close to midnight still working on a problem because it's so fascinating. And this kind of passion, that is a magic weapon with the customers. And also you want to be part of a team that shows this enthusiasm, shows this joy, and it's like if you go in a restaurant and you see the waiters, it's a really good atmosphere. You want to go there. You want to be part of that. But if you see that they're arguing between each other among themselves, this cannot be good. I'm out of here. Exactly the same applies to companies.
Well, you've mentioned food, and I think that has triggered grumbling stomach. So I will pass it back over to Ignacio for a few final words. Thank you very much, Erich. And Ignacio will thank you again, I think, in just a second.
Thank you very much. This has given a complementary view on what is modeling and research in this context of industry. So thank you for attending. Thank you for being here. And as we were saying now, for those of you who are here now, we have an apéro. The apéro today will be in the building that is basically you living to the right, and it will be facing to you, Amphimax. And I'm sure that as we enter there, we will identify exactly where the tables are, and we can meet there. And Erich and Bill will join, so you can continue the conversation around some food and drinks. So thank you very much.
Thanks.